Earlier on in the course, we talked about families of sets where the intersections have to satisfy certain restrictions, in particular the restriction of being non-empty. Now we're going to talk about also families of sets where the intersections have to satisfy certain restrictions, but now we're going to talk about the restrictions are going to be that that the intersections shouldn't have certain sizes modulo certain primes. And also sometimes that the sets have also a bound on, a restriction on the sizes of the sets, as indeed we did when we talked about, for example, the Erdős-Colorado theorem. I'm going to start, in this video, I'm going to discuss a particularly simple example of this, but also a particularly sort of striking application of a dimension argument. And more generally of the use of linear algebra to prove results in combinatorics. And the question is the following. So supposing I have a set system. I'm going to ask lots of different questions all at once. So suppose that every A and A has even, odd size, and for all A, B in A with A not equal to B, A intersect B has even, odd size. The question is how large, as always, or as often, how large can A be? So actually we've got 4 questions. We can assume that all the sets are even and all their intersections are even. They're all even, their intersections are odd. They're all odd, their intersections are even. They're all odd, their intersections are odd. And what we're going to see is that the answer to the question is dramatically different according to which, well, the questions, those 4 questions split into 2, and the answer is dramatically different depending on which of the 2 classes. And actually the 2 are, either we ask for the intersections to have the same parity as the sizes of the sets, or we ask them to have different parity. It turns out that having different parity is a vastly more restrictive condition to place. But let's just think about some examples first of all. So let's have a look at the even case. We can take A to be all sets such that, or sets, say, A such that 2i minus 1 is in A, if and only if 2i is in A. In other words, all unions of 1, 2, 3, 4, all unions that you can make by picking some of these sets and putting them together. Because obviously they're all going to have even size because we pick them in pairs, and all their intersections will also be unions of these, so they'll also have even size. So this gives the size of A is 2 to the n over 2, except if n is odd, we can't quite take n over 2, so I'll take the floor of n over 2, the integer part of n over 2. How about odd, odd? There we could take, let's say that 0 belongs to the set as well, so we could have 0, 1, 2. So I'm just going to put 0 into everything. 0, 3, 4. 0, 5, 6, etc., etc. So, and then I take unions of these. So I can say that more economically. So I'll take sort of A dashed equals the set of 0 union A such that A belongs to A. And then if I take any set A, I've added one element. If I take any intersection of two sets A, I've added one element. So everything's become odd when it used to be even. And so now I get 2 to the n minus 1 over 2. How about odd, even? Well, let's just sort of write down a few and see what happens. So 1, 2, here are some sets of odd size which clearly have even intersections because they've all got empty intersection. Now, can we add anything else? Oh, no, we can't. So we can't add the empty set because that's not got odd size. And any other set that we add will intersect one of these in a singleton, which will not have even size. So we're stuck. We've got up to n. So we can take that anyway, and that gives A equals n. What about even odd? Well, again, we can do the same trick of just adding an extra element. I think I won't make it that extra element 0. I'll make it 1 this time. So we can have the sets 1, 2, 1, 3, all the way up to 1n. Can we add anything else? Actually, that depends. So if n is odd, then we'll notice, add the set 2, 3 up to n, because that intersects each of these sets in a singleton, which is odd, but it has even size because n was odd. But if n is even, we can't add that set. And in fact, it doesn't take more than a moment to see that if n is even, actually we can't do better than, we can't add anything else because it's got to intersect all of, yeah, I'll leave that to you, I think. So we seem to get, in this case, A equals n if n is odd, and n minus 1 if n is even. And a little sanity check for that last thing is, supposing n equals 2, how many sets can we choose? Well, if we choose the empty set, then we can't choose anything else because that will have an even intersection with the empty set. And if we choose the only other set of even size, which is 1, 2, we can't choose anything else because we can't choose the empty set, and we can't choose a singleton because that won't have even size. So we only get one possible set when n is 2. So that actually agrees with this bound. Notice that these are just lower bounds, so I'm not sure that I can't do better, but at the moment, that seems to be, we sort of get stuck with these examples when we reach n sets. And then if you play around, you'll find that keeps happening. And the point is going to be that this is actually true. So the same parity examples, you have exponential sized set systems, but for different parity, you only have n sets, or even sometimes just n minus 1. So let's give some proofs. So main proof idea, and I feel a bit sad telling you this because it's a very nice exercise to come up with this idea. My only comfort is that this is sometimes set in, at least in Cambridge, as an exercise in undergraduate example sheets on appropriate courses. So I hope that at least some of you will have seen this without having been told how to do it before. But for those who haven't, I'm sorry, sometimes you just have to spoil problems. There are plenty of other problems that are unspoiled, including some on the question sheet. So there we go. What is the main proof idea? It is associate with each set its characteristic vector. considered as an element of, now remember there's a dimension arguments, f2 to the n. So we take a 0, 1 sequence, namely the characteristic function of the vector or the character, but we think of it as the zeros and ones as living in f2, not in z. So now let's just observe that the conditions that we're putting here are linear algebra conditions. So we get that, so define a bilinear form on f2 to the n to be a sort of an inner product. So xy equals sum xi yi. This is mod 2. So the even thing, the condition is, the sort of equivalent problem is, how many vectors can we choose? Oh, by the way, yes, sigma xi yi, if x is the characteristic vector of A and y is the characteristic vector of B, then we get a contribution here precisely when I belongs to the intersection of A and B. So this thing here is precisely the parity of the intersection. So how many vectors can we find in f2 to the n such that it's quite convenient to write this xy equals 0, or sort of how many vectors, or how large a set x of vectors. Okay, let's write it as for any two of them. And notice that I'm now allowing y to equal x. So x inner product, so to speak, x inner product x gives me the parity of the size of x, which I'm also assuming is 0. So we just get this convenient condition here. So there's a very, very simple way of answering this question. So we just say let x be a set of vectors satisfying the condition. Let x1 up to xk be a maximal linearly independent subset of x. So we can make one observation completely immediately, which is that if there's only k independent vectors, then x lives inside a k-dimensional subspace. So observation 1, x has size at most 2 to the k. So since x lies in the span of x1 up to xk. But we get something else. xi equals 0 for all x in x and I. So x lies in the orthogonal complement, so to speak, of this subspace. Or to put it a slightly different way, every vector in x satisfies k linearly independent conditions. And so that tells us x has size at most 2 to the n minus k. So it's got size at most 2 to the k, size at most 2 to the n minus k. K is an integer, so size of x is less than or equal to 2 to the n over 2 as desired. The odd case, actually, at the moment that I'm lecturing, I'm pretty sure that this is the best example, but I haven't actually checked. But I've decided that that would make a nice question on the example sheet. I've actually just added it. So there are 14 questions on the example sheet. Earlier versions had fewer questions. So if you've got a version of the example sheet with fewer than 14 questions, there's a slightly updated version now. I want to go straight on to the odd even case, which is reasonably simple. So here we have that, so translating it into vectors, how many vectors can we choose? If x, y is 1, if x equals y, and 0 if x doesn't equal y. And, well, we've got our favorite delta xy showing up. And so the answer is at most n, since these vectors are linearly independent. I'm not going to write down why they're linearly independent because I really feel that you should have enough linear algebra to be able to prove that they're linearly independent, but I will at least say it. If you take some linear combination of the vectors, you just zap it with x. That tells you the coefficient of x. And so if that combination is 0, that tells you that all the coefficients are 0. It's just the usual proof of independence in lots and lots of different contexts. Okay, so that was pretty quick. What about even odd? I'm going to do, so first let's suppose, because you remember that in the even odd case, it was a little bit weird. The examples we had depended on the parity of n. So let's deal with the case where n is odd. So suppose, not sure what that f is doing there. Suppose n is odd. Then replace each a in a by its complement. Then what do we get? Parity changes because n is odd. That's the parity of the size of A. And also we'd like to be able to, we want to get back to this case here. So what I'd like to say is that the parity of A intersect B also changes. Let's just quickly draw a picture to see why that's the case. So here's A, here's B. And A and B have the same parity, which tells me that this set and this set, so here's A, here's B. So A minus B and B minus A must have the same parity because I've removed something of the same parity from A and B. I don't even care what that parity is. Because n is odd, and the union of those two parts is even, this and this must have different parity. But this bit outside is the intersection of the complement of A with the complement of B. So this outer part has a different parity from the intersection here. So do the parities of the intersections. So now we're done by the odd even case, which I've just done. And now if n is even, we're going to do a little trick. Replace each A by A complement if n belongs to A, and just by A otherwise. So the second replacement is a trivial replacement. Replace it by itself. So replacing A by A complement does not change parity, either of A or of any A intersect B. Let's just see why that last one is true. So here's B, here's A, and I've replaced A by A complement. So what's happened to A intersect B? It's gone from this set here to this set here, but B had even size, so those two sets must have the same parity. So the only thing that could go wrong actually is if I have accidentally replaced two sets by the same set, and that can only happen if I had a set and its complement both in the original set system. But, oh, that's not but. Note that A does not contain any complementary pair. In fact, we can say something a lot stronger than that. It doesn't even contain any pair of disjoint sets because all the intersections are odd. So the new set system also satisfies even odd, is of the same size, and consists of subsets of n-1. And so therefore, by what we've already done, in the odd case, we get that the size of A is at most n-1. That last sort of fiddly thing is not really the main message of this part of the course. The main message of the part of the course is we associated sets with vectors, show that the vectors were independent, and in that way we got this very, very strong upper bound on how big the size of A can be. And up here, when we were doing the even case, we didn't, it wasn't quite as simple as just, so getting some linear independent vector. The proof was very simple, but it wasn't just associating each vector with each set with a vector and showing that the vectors were linearly independent, but it was using some very simple linear algebra. Okay, I'll stop there for this video, and in the next one we're going to start talking about intersections mod P, where P is an odd prime, and there things start getting very, very interesting. Not super hard, but very, very interesting.